Good evening, everybody. Today is our last day we're going to be spending on colligative properties. So we're going to be working pretty hard through some challenging problems. I'll try to keep time in mind because I do want to get through a number of problems and some topics at the end. So Monday's class is going to be starting on kinetics. We're starting a new topic on Monday. There will be a little bit of that in the exam. So in order to make sure that you guys are feeling comfortable with that, your supplemental instruction this week is POGIL Activity 36, which you have in your hands. Unfortunately, they came out stapled together. 37 is what we're doing in class. So if you look at that packet, it's stapled together. It's really thick because half of it is the supplemental instruction, Activity 36. The other half of it's in-class Activity 37 that we're doing in class on Monday. So I was going to tear it apart, but that was a pain. So make sure that I know that I said that you're only required to do 3 out of 4 supplemental instructions. Make sure this is one of them. I will start class on Monday assuming that everyone has completed POGIL Activity 36, either in supplemental instruction on Thursday night or Saturday day, or on your own, ideally in a group outside of class of some sort. Any questions about that? So try to complete POGIL Activity 36. Manu and Mohammed, can I have you guys sit up here, please, today? Thank you. Yeah.
How does the Saturday thing work? Because I got to work like Thursday.
You got to what?
I have to work like Thursday at 4, so...
Yeah, so there's just a link. You just click on it on a computer that has a webcam and microphone, and then you log in, and Josh and I, or Josh, will run the session. You'll break out into small groups, and there'll be a group of 3 or 4 of you. You'll be working on activity just like you'd be doing in person. And then Josh or I will pop around to each of the breakout rooms and see how you're doing and answer questions. So it's very much like an in-person.
How do you download something so you like
Yeah, do it like a minute before, and then it automatically asks you to do something. It's a light client. It populates really quickly, and then it removes itself if you don't use it. Or you can download the software if you want. All right. So let's get started since we have a lot of different concepts and questions that we're working with today. This is a question that would be very similar to something on an exam. A lot of the questions today are, you'll notice in the very back of your worksheet for today, there are a number of things that you might find useful for our class. And then the second to last page has some additional practice problems that you can use to prepare for the exam. Alright, so for now, let's get going on this, and I don't want you just clicking in, yes, it's possible, because who knows. I want you actually figuring out how you can answer this with certainty.
Yeah, but online right now,
Just make sure you know what
I don't know where you're going. Yes.
is that right? Are you sure?
Yes.
You're not making me
Still wanted molality, and then it wanted to increase right there. For some reason, it's not perfect, then maybe 1 or 2 longer.
What am I going to complain about?
All of them.
gas if you don't put the units, trust me.
Yeah, that's all it's
I know gas off.
But it is random.
liters of atmosphere over Kelvin.
Okay. Okay, I'm just sarcastic. I need to write this so we can have the last. But we do have winner. So, yeah. So you know here's a pie, right? I feel like I'm really lost. That's a pie. You're using osmotic, right? Yeah. Yeah. No, that's not answering the question.
That's what I'm doing. Now we know
Did we multiply by I?
All right, we have 39 responses. Maybe I should mention this. I guess it's not really as important for you guys because you're in the room. Moed? Thanks, man. Is it okay to log in when you're not in class and participate in the clickers?
What? No.
Let's not do that. So that is academic misconduct because you're basically claiming participation when you have no idea what's happening in class and you're just seeing something pop up on the screen. So I use that to keep track of who is here when. For when people ask me to write letters of recommendation, and I can talk about attendance and then correlate that with emails I have about, did they communicate with me when they weren't here, those kinds of things. So like some intangibles that you don't get from a grade in class, right? So just make sure that you only use the iClickers when you're here. I can put up geofencing, but then it becomes a pain to log in. So I would prefer not to do that if I don't have to. If I feel like I need to do that, I will. Yeah.
Just a logistics question. What if we're walking to class?
Then just do it when you come here. Don't answer questions if you're not here.
Okay.
That's like saying you're doing something you're not doing. So you only need to answer 75% of the questions for the day to get credit for participation. And it's only participation based. It's not right or wrong, as you guys know. All right. How do we approach this problem? Can I hear from different people throughout the day? Kayla, thank you for being my first volunteer today. The supplemental instruction leader who's going to be leading our supplemental instruction Thursday and Saturday? Yes, he is a fantastic resource.
I found the best pop factor and
Whoa, let's go way back. You're diving into finding a value. So what do you mean? Why is the Van Hoff factor important? What are you using it in reference to?
well, the best pop factor gives you a rough amount of the ions in ionic compound, and you use that to compare to what the Van Hoff factor of calcium chloride is.
Okay, so Van Hoff factor is how many particles something dissolves into, whether it's one particle for one particle or multiple. So what would you expect if we're using calcium chloride to be your Van Hoff factor?
3.
All right, so that would mean that you need to be familiar with your polyatomic ions. If you are not, on the next slide or second slide I have where you need to go to do that, but you were not allowed to bring those onto the test with you, so you need to have those memorized. All right, so calcium chloride, CaCl2, forms 3 ions when it dissolves. So then what do we do with that information? How does that help us answer this question? You said you compared it to something, but I don't quite...
Oh, I solved for I using the amounts over here.
Solving for I, what is that? Is that like a computer program? What's that?
The I in osmotic pressure.
Oh, okay, so we use an osmotic pressure equation. What's that equation?
I IMRT.
Is it big M or little m?
Big M.
Okay. And you solved for I in this equation. So what did you use for pi?
4.14.
Okay, so our osmotic pressure, so 4.14
Atmospheres.
equals, and then you said you're solving for I, so we leave that blank.
0.0250 divided by 0.398 liters times the gas content,
What's that?
0.0821 roughly, times,
What? I think we missed something.
you want me to say all those things?
Yes, please.
Of atmospheres divided by the mole times Kelvin.
Okay, a lot of people are leaving these out. And this becomes a big problem when I give you on the test multiple variants of R. R can be given in tons of different units. It's the same variable, same constant, but you can have it instead of atmospheres. You can have torr, or you can have millimeters of mercury. And this number is different, but it's the same unit. You just need to make sure that whatever unit you have here matches your unit here. All right? It's really important. And then our last value we're multiplying by?
Times 296.15,
Where'd you get that?
23 degrees Celsius plus 273.15 Kelvin.
And because we read out our units for R, we know that that needs to be in Kelvin. So this really guides us to what units we need to use. Okay? So that's great. We can totally do that. If you do that and you solve for I, what do you get?
2.71.
Ooh. What does that mean? Love?
I said it is possible
Why?
because the I is I did it a different way.
Okay, so don't worry about that. Let's come back to that in a sec. So what do we do with this information with the 2.71 being the Van Hoff factor?
It's the way I did it was I solved the ideal with the I is 3 because I did the amount of ions in calcium chloride.
Okay, and so you came up with a mismatch as well. And we'll talk about the process in a second. But first I want to focus on what we do with just this number. Leah.
If all of the ions didn't dissociate,
Can everyone hear her?
it could be.
You say it a little bit louder, the same thing?
If all of the ions don't dissociate, I suppose it could be true. It could happen.
So can this number, is this number bigger or smaller than what we expect?
Small.
Is that okay?
Yes.
Could it be bigger?
No.
What if it was 3.3? Is that okay as well?
No.
Is that a rounding error? No. Okay. As long as we trust the people who do these measurements, then that is not okay. That would make this, no, this isn't possible. But because the Van Hoff factor that we found, the actual Van Hoff factor, is less, it means exactly what Kalia said, that it means that out of those 3 ions that could separate, 70, 80% of the time we find them separate, the other percent of the time we find them together. So there's still some attraction between them that isn't overcome by water when we dissolve it. So the other approach, what's the other approach that we can do to answer this question? That would give us the same thing. Christina?
I multiplied, I didn't use the same equation, but instead of solving for I solved for the pi symbol.
Great. So what did you use for your I?
3 because calcium chloride is Ca and Cl2.
Okay.
3. And then I used 0.0250 moles over 0.398 liters. And then I multiplied it by 0.082056. Yeah, liters times atmospheres over moles times kelvins, and then I multiplied that by 296.15 kelvins.
Okay, and once again, we're going to go through and make sure all of our units actually cancel out. Kelvin, atmosphere does not, so I shouldn't have crossed that out. Moles cancels out, liters cancel out, so we're left with atmosphere on the right side, and we can solve for what our theoretical osmotic pressure would be. And what did you find?
I got 4.58 atmospheres.
Is that okay? Does that confirm what we talked about before? Why or why not? Matt?
It's the same thing. If it was measured at 4.14 and 4.58 is ideal, then it's less than but close to.
So it's generating a little bit less osmotic pressure than we expect, which means there's a little fewer particles in solution than we'd expect. What is the ratio of 4.58 over 4.14? Did anyone do that math? Take a guess. Anthony, say nice and loud.
2.71.
2.71. All right, so we get the same answer both ways. That we see that the theoretical Van Hoff factor is not quite the actual Van Hoff factor. So would we call this compound soluble, calcium chloride? Does that count as being pretty soluble? Yeah. So if it was down at like 1.4, we'd be like, no, it's not very soluble. Like it does dissolve a little bit, but not that much. All right. So this is one of the ways that we can use osmotic pressure to figure out the identity of a substance. So I might give you multiple substances and say, which one is this? So you'll need to know what the formula is from the name. You'll need to be able to figure out the Van Hoff factor from the formula. And then you'll have to figure out, with all of that information, if that could be the actual substance we're looking for.
What range would we be looking at for ATM to know that it's like within, because that's 0.4 of a diff, or 0.44.
So that's a little bit irrelevant, is the 0.4. The more relevant thing is the ratio between the two. So this number 4.14 divided by 4.58, that's 2.71. That's close to 3, right? So the closer together these two numbers are, the closer the theoretical is to actual. Right? So it's the relative value here. If we expected to find 4.58 and we found 1.01 atmospheres, we'd say that that's not really soluble because it's basically atmospheric pressure.
Okay, I'm trying to understand here, and I did the 4.58 over the 4.4, right? Is that what you said?
Yes.
Because you'll
I'm
get
not getting that.
something.
True. Okay. So I probably stated that wrong. Can anyone help correct what I just said?
It's going to be the same as the ratio of your 3 to the 2.
Thank you. So thank you for pointing that out. The ratio of 4.58 over 4.14 is
0.9039.
9039. If you do 3 over 2.71, what do you get?
0.9033.
Sorry, that was bad setup on my part. Any questions on that? So the relative ratio should be the same between this.
But osmotic pressure measured can be less than theoretical? Or
Any of the colligative properties can be less than what's theoretical because the Van Hoff factor plays into that. And if the Van Hoff factor is not actually what it's expected to be, all of those colligative properties will be diminished in their output. Yeah. All right. Could you see doing this on an exam? Do you want to practice some of these then? Okay, we're going to do some harder ones. But this is something that'd be really good to practice. And as you saw, there's multiple ways of going about these types of problems. So if you saw one way and you're like, I came to the same answer, but it wasn't the same as either of those two, if you can justify it, that's fantastic. So a couple notes on the exam. I'm only spending 2 minutes on this at most, and then everything else can be done in Blackboard discussions. So for those who haven't been in my class before, I do allow you to bring a note card to the exam, 3 by 5. It can only be handwritten. Thank you. You want to show that off, Logan? All right. So just a regular size note card. I just don't want any oversized note cards. Some people write crazy amounts on there. What I find is that most people actually don't use the note card during the exam, but it helps focus you in your study. It helps you distill down what's the most important thing I need to remember for the exam or I need to be comfortable doing. That's why I use them as a study tool. And then if you get stressed out during the test, it's a crutch that you can lean on if you need to. The exceptions for that polyatomic ions, strong acids, and strong bases. They're listed here, table 2.4 and 3.1 in the Sengate's book that we have. You need to be comfortable with those. If I give the name of one of those polyatomic ions, you need to be able to write the formula, know the charge, know if it's a polyatomic ion, or if it's an individual ion, chloride versus chlorate or perchlorate. You need to know that if you put chlorate into water, it will give you ClO3 minus, not Cl and an O and an O and an O. One way to help with that is to draw the Lewis structures of all of those as well. So it's a nice way to kind of make sure you can kind of see what it looks like and know what it represents. Bria?
Okay, so last semester we had the solubility sheets. Are we not getting those in GCHEM2?
Did you see what's on the back page?
Oh, okay, never mind.
So I am on the fence about giving you a solubility chart for the exam. The question is whether you guys want to... The more information I give you, the more you're going to have to do with it, right? So the question that Avery asked is, how far am I going to ask? Like, how different are those two numbers, and then how is that going to impact whether you say it's soluble or not, and how you answer different questions? We'll talk about a question here in a minute that exemplifies that, and then we'll make a decision on whether I provide you with that chart or not. If you're not familiar with the solubility table, one nice thing is just kind of think about what is always soluble, what combinations are always soluble, or what individual cations or anions are always soluble. And that's just useful to keep in mind. It's way faster than looking at the table. So look at the columns that are all white across, either horizontal or vertical. What are those ions? And then that'll kind of give you a leg up when you're answering some questions. All right, our exam is 75 minutes because we have a longer class, which is great, instead of 50 like I had in the fall with some of you. So what does that mean? Does that mean that you guys have longer to take the test, or does that mean that we do more in that time?
We do more in that time.
I am very interested in doing the last 15 minutes of it as a group test. The challenge is going to be space, so I'm going to find out what time that class finishes, and if it's available in the last 15 minutes of class. As you finish here, you will migrate into that room, and you will be put in groups of 3 as you walk in there, and you'll get a group version of the test. It's the same questions, but it'll be a scratch-off, and we'll explain how that works that night. And you'll basically have to scratch off the answer out of 5 options. It'd be like, think of a lottery ticket. So it has answers A, B, C, D, E, just like a multiple choice. Your group has to decide on the same answer that you want to scratch off. You scratch it off, and you get the most points if you get it right the first try. If you don't get it right, you'll see it. If you get it right, you'll see a star underneath that. If you don't get it right, you have to recalibrate in the group, justify why that answer was wrong, what the right answer is, and then you get to try a second time. You get a little bit fewer points if you do that. And so basically you can go through this process, and I take the hardest questions on the test, and I put them as like the 5 scratch-off questions. The reason I really like it is because you leave the test knowing how you did on those 5 hardest questions, and you also get to learn a little bit from other people in the class. One of the reasons I don't like it is students leave oftentimes, they're like, I got all 5 of them wrong. But it's the 5 hardest questions, so it's like, okay, you got the 5 hardest questions wrong. That doesn't say what you did on the rest of the test. So there's pros and cons. The other thing is time, right? So what I typically do in that case is, if you do better on the group portion, you write your names on it, right? All the group member names. If you do better on that portion of the test, it counts for 10% of your course grade, or the exam grade, sorry. If you do worse on it, it doesn't count towards your exam at all. Peter?
I am afraid that that extra 15 minutes after the test may eat into some of the very difficult lab.
It is part of the 75
So
minutes.
we're going to take 60.
Correct. The exam would be 60 minutes, and then the last 15 would be, or if you wanted to spend the whole 75, if we have 2 rooms, then you can just stay work on the exam the whole time. If you finish early, you could go to the other room and then do the scratch off. That's what I'm hoping to do. I'll find out if that room is available Wednesday nights at that time. Aaron? I think we're way over 2 minutes on this. So, really quick question.
Their class ends the same time ours does.
I see them out way earlier sometimes, though. So maybe that's not very useful. Okay. So that might not be an option. In that case, we'd have to stop 15 minutes early. Everyone turn in part of their exams, and then you would get to work on the second part. So stay tuned. I would love to do that. I think it's a great learning opportunity, and you guys get at least know how you did on some of it. Last thing. I don't want people to be anxious not knowing what my exams look like. So I posted all of semester one's, well, not all, 3 of the 4 first semester exams up there. So they're in Blackboard under additional resources, I think. There's a folder there for Gen Chem 1 exams. I also posted my previous Gen Chem 2 exams from University of Delaware. What that means is that we may have had a totally different order of topics. We might have other topics that were in there. But it'll give you an idea of the types of questions that I asked on some of these topics. So you might need to look between exam 1 and exam 2 for some of the things that we're working on now. But it's a resource you guys can use, and so go pick the questions that seem relevant, and you can work through those as practice. All right. So, 27 minutes into class, 26 minutes into class. My goal for you guys today is really I want to work on this, for the most part, determine the identity of an unknown through finding its molar mass for any of the 3 colligative properties that are listed here. Raoult's law is a bit different. We could still do that as well, but we'll be talking theoretically about this, and then in theory you could extrapolate as well. And then I want to kind of take some of the colligative properties, think about intermolecular forces and how that relates to climate change and concentrations of CO2 in the oceans. So increasing global temperatures in relation to atmospheric CO2 concentrations, how those two influence ocean CO2 levels. Hopefully we'll have time for that. As much time as I want. All right. So we have one question on Raoult's law, and this does relate to the other colligative properties. I believe you have this question 2 on your worksheet, and you have the image as well. And if you're having a hard time seeing, you can zoom by pinching in on your iClicker question. Good question. So these 2 chambers of water are separated by glass, and they are enclosed. So this is a box that is closed to the outside atmosphere. There's a glass wall between these 2 that is not permeable. So this is not about osmotic pressure. This is about vapor pressure. Raoult's law. So think about evaporation, what's happening on both sides, how that's influenced by solutes on the right side of the seawater. What's going to happen if you give it an infinite amount of time? What are you going to expect to see there? So this class is always very interesting to do clicker questions in because sometimes you're very surprised by the answers. So there's two very different answers I can think of why people would come to the answer that is the majority answer right now. So I'd really like to hear from different people in the class as far as how you got here. Madison, did I see you potentially raising your hand to answer this?
No.
To share your thoughts?
I mean, I will, but I wasn't.
If you'd like to, that'd be fantastic. So what process do you go through to figure out which one of these answers and why?
I was thinking that the pure water was going to evaporate more quickly because seawater obviously has stuff in it. And so I was thinking that the water was going to move to the right side.
Okay. And when you say evaporate more quickly,
Okay, wait, what's the question?
how do you... So is there anything in the image that helps support that?
I mean, it pictures more molecules outside of, or on top of the water level, but I was also thinking that since there's going to be salt and other things dissolved in the seawater that we've talked about and not evaporating as quickly.
Okay, and actually specifically during office hours, I think we had a conversation about this, right? So how does the mole fraction of solute influence
The more
the evaporation?
concentrated the solution, the lower the evaporation rate. I just made those words up, but
No, that's pretty awesome. So let's take that, and we have a couple hands of people who really want to share. So Logan, you first.
Okay, so since we talked about this last Wednesday about ions not letting, like, increasing the vapor pressure, so it like makes a sort of like a barrier, sort of kind of, so they can't like break free. They can't break it in more molecular forces easier because they bounce off the ions.
Yeah, and so we want to be careful about saying that the ions are attracted to the water, right? Because it's not about what they are; it's about how many.
But something else in the image is you can see by like the arrows. It's like there's less blue arrows on the right side. So
And those are the evaporating ones? Yeah, fantastic. So I think a lot of really good points are made here. So the more solutes you have, and the reason I love the fact that it's mole fraction that they use to describe this, is that mole fraction, there's a lot of stuff on the board. So mole fraction, the way Raoult's law is the partial pressure of the, is it solution, equals the mole fraction times the partial pressure of the solvent. If it's a pure solution, what's the mole fraction of solvent? 1. So the pressure, vapor pressure of the solvent times 1 equals, right? So it's the same. No solute, no difference in pressure. As more solute is in there, what happens to the mole fraction? It becomes smaller, right? Maybe 0.97, 0.95. And then that's directly related to, exactly proportional to the vapor pressure of the solute. And so going back to the description, that the surface, the water molecules not only have to have the right speed, but they also have to be able to get to the surface of the water. So if there's more things blocking the surface, a larger proportion or percentage of the surface is blocked, that proportion of molecules don't evaporate. So if you give this enough time, you will have only molecules of water on the right side. Because of the differing rates of evaporation, you have a larger rate of evaporation on the left side than the right, and so you end up with an equilibrium process that is faster to bring molecules in on the right side. This also helps describe why it is you need a higher boiling point, right? So the increase in boiling point of a solvent is directly related to Raoult's law of increase in vapor pressure. You need to have more energy then because the surface is blocked by more things in order to increase the boiling point of the solvent or the solution. All right, that's really all the time we're going to spend on Raoult's law and vapor pressure because it ties in everything else, but I want to spend more time on a couple other things. All right, so on your paper, I think you have a question. How does osmolarity relate to molarity? So here's our definition of osmolarity. And let's look at a couple examples. Osmolarity of pure water is 0, as expected. If you have a 2 molar solution of sucrose, it's 2 osmolar. What if you have a solution 2 molar sodium chloride? write down your thoughts as to what the osmolarity of that solution is. All right, can I have a new voice guess? Aaron, why would you guess 4?
Because osmolarity looks like it deals with individual particles of something dissolved in water, whereas molarity deals with the whole molecule.
Great. So molarity deals with the parent compound, and osmolarity deals with the particles. So is there a mathematical relationship that we can write to define osmolarity in relation to molarity? Go ahead and write it down on your paper. A mathematical relationship between molarity and osmolarity. For osmolarity? I don't actually think there is. I don't know. You can Google it. Maybe there is. Any reason why I'm talking about osmolarity? Has anyone come across osmolarity before? Love?
Isn't it technically in the osmotic pressure?
It is an osmotic pressure formula, but also I believe in a number of medical applications you can talk about what the osmolarity of a solution is, because that's much more relevant than what the molarity of the solution is. All right, so mathematical equation. Who has one that they want to share? Colin.
I just said osmolarity equals molarity times the number of individual species.
Okay, do we have a more defined term for the number of species? Or Tyler? Molarity times Van Hoff factor. That is the osmolarity. All right. Let's have fun and challenge you guys and talk about a number of factors here in a second. Working on question number 4. All right, 30 more seconds. All right, let's take a look at the answers. Woo! All right, congratulations, 4 people. Why? Why might we answer E? So let's have one voice at a time. Go ahead.
It has more ions.
Great. The Van Hoff factor is higher. It has a Van Hoff factor of 5. Everything else is less. So what gives? Why is that wrong? Colin?
It's insoluble.
Insoluble. So this is what I'm talking about. If I give you guys a solubility table, you need to use all your resources. Okay? So are there more than one possible answer then?
Yes. Yes.
So what are the answers that are next in line, and how would we determine which one of those might be? Love?
I checked, well, my choices were limited to the B, C, D, and A. But I actually took out B because that's only 2.
So Van Hoff factor of 2 doesn't compete with the others that have Van Hoff factor of 3. And then what do we do?
Then I went with weight. With the molecular weight.
Why?
Because isn't it like if weight is increased in solute, then it has a greater effect? Or something.
So if there is more mass of a gas, you have more solubility because the dispersion forces are greater. I don't know if that's where you're going with that. Not necessarily relevant here. So now it becomes really hard. This was originally disodium oxide, and I kind of wanted to leave that in there, but it reacts, it spontaneously combusts once it forms. So that would be pretty fun. I would be fine with any of these 3 answers, honestly, if you gave those. But the one that I chose, if you look at those trends, right, which ones are always soluble? Nitrate is always soluble. What about chloride? Are there any exceptions for chloride? There's a couple. So that's a little bit less soluble typically. And what about sulfide? All right, and so I kind of extrapolated from those trends. I don't need you guys to get to that level of distinguishing between them, but I think you could if push came to shove. So the question is, do you guys want the solubility table in the exam? You have to use it if you get it, right? My dream would be to use open notes tests and make them really hard, and you guys have to figure out how to use the information, because that's really what we want you to be able to do, and that's what you want to be able to do. Colin?
Are you going to be asking us questions with things that are insoluble?
If I give you the table, yes. If I don't give you the table, I'm not going to ask you to memorize this table. All right, so I will ponder on this particular point. I do like you being able to use multiple sources of information to answer a question. I will see whether it's worth the time that I know it will add onto the questions if I do. All right, I will try to pay attention. All right, so can I get someone to read the 2 parts of the next question out loud? Bria?
Medical researcher is analyzing patient blood for a mutation in hemoglobin that results in sickle cell-like disease. This mutation in hemoglobin can be detected by an increase the molar mass of the protein. Determine if the patient has the Bangkok J hemoglobin mutation.
All right. Next person, read. Ruby?
A physician dissolves 21.5 milligrams of one variety in water to make 1.50 milliliters of solution at 5 degrees Celsius.
I love how you use one of them with all the stick figs and the other one you threw it away.
Okay, she measures an osmotic pressure of 3.614. What is the identity of the protein?
All right, and you guys have a list of the 2 different proteins. So let's see how you can use Archuleta properties to identify substance. Take a minute, read through this, and see if you have any specific questions. I'll wait 1 minute before I answer any of those. And this is question number 5 on your worksheet.
We can change it to atmosphere, so you just divide it by 60.
I know, but that's what I'm saying. We don't use that, right?
All right, is there anything you guys are not familiar with in the question that you need to figure out what it is?
Yes.
Mohammed, what is that?
KDA.
What is KDA? What does K stand for? Kilo, which is 1,000. All right, so it's 1,000 Daltons. Biologists like to use the term Daltons instead of grams per mole. So if you go do research in a biological lab, they'll say this protein weighs 14.2 kilodaltons. That's 1,000 grams per mole. So are these little or big molecules?
Big.
63.4 thousand grams per mole and 68.8 thousand grams per mole. Those are the molar masses of those two different proteins. All right, you know how to start going about this question now? Daltons is grams per mole, correct. So go ahead and try to figure out what equations you have, what your knowns are, what your unknowns are, and line it up. If you get stuck, talk to the person next to you. If you're still stuck, raise your hand and ask one of us. It's a protein. So can you make an assumption about proteins? Fair point. One other assumption that you need to make is whenever you have a protein, there's an assumption about the Van Hoff factor. You assume it's a molecular compound, a Van Hoff factor of 1.
We'll get this, we have it, and then this will go into that. That, right? And then we'll just be finding. Am I right?
So, should we just solve for moles and then convert the moles into grams?
Yes.
Right? So, it's going to be M 0.21 and then T, which is 278.
No, wait.
And if you guys look at the back of the page, there's a lot of information there that you might need throughout the class. There might be
That's the R factor.
conversion factors, there might be constants.
I converted it to ATMs.
And that's 7.
You divide by 760. So you have 3.614. You have 764s is 1 ATM.
It is open for discussion.
Okay, so I found molarity.
I thought of finding it a different way.
Can you do?
I'm just saying, I thought of doing this. This is when you take
You're talking about.
grams. This is this, right?
How would you know? Oh, you're talking about this is picking. You're talking about picking one.
And just proving it? Yeah.
You guys act like I know what I'm doing.
I said it first and then you started saying that, so I was like, maybe you knew where you were going.
Wait, what you said?
Me?
Yes, it made sense, but I just couldn't.
Okay, so this has grams now.
Takes a moment.
Yes, this has grams now. And this you can also turn into grams.
Yes.
So then when you multiply times this, you get
Yes.
That's what I'm trying to figure out. Oh, calculator. This right here should be. I'll calculate it on this one. I think it can be real powder, but you can't. Yeah, alright.
Peter, can you send us like the right path? You done?
Sure. Okay.
Remember that's milligrams, not
I is, right? 161. Disqualify I, right? Because it's just one. And then we can go ahead and divide by.
So it's gonna be
We have to use meters.
point
That's the R.
Yeah.
So divided by 0.61 by 0.0861, right? That's essentially like dividing.
this is how you split up, right?
By
And you would multiply it times that. I'm doing it. That's how you split it out, right? And then oh wait, I didn't put the value.
There's 100 milligrams.
I know what you're getting at.
Yeah.
Well, that's not it.
I like what you're getting at, because I feel like I can just
Just tell me.
Yeah. So you want to have math on actually write things down, right? You can go back and sometimes you don't have to put as many things in your
So we get a really weird right.
Well, and just right.
So it's milligrams per gram. But
that's why it helps.
so
Yeah.
Yeah, but it's not matching the things.
Maybe later.
I kind of forgot about the color.
The numbers, Mason, what do they mean? Sorry, I'm
Yeah, this is working for me, so I'm going to go back to my round. I'm getting numbers and the setup seems right, but the numbers still not.
I'm still going to go with bank.
I'm just going to convert everything.
So it has been pointed out to me that an error that I've had in previous classes has been corrected on the screen, but not on your worksheet.
Wait, what?
Sorry.
Oh,
So we have.
Oh my goodness. I got the swing.
I knew I made a mistake on this before. I was going through my slides today. I was like, yes, it is right. And I must have corrected it only in the slides and not in the worksheet.
Okay, but that means I was right. They called it right. Sorry.
Alright, so I'm going to give you guys 30 more seconds just to, if you've started to write it out, write things out, write out the process, and then we'll work through it. Don't you thinking there's multiple ways to answer this?
That's fine.
So I was right. Bank costs the most, as it should be. Which unfortunately means that we just technically should have it. So this is easy.
So, do was not our way?
Alright.
I did.
The heart and soul of working through a problem like this is figuring out where to start. If you don't figure out where to start, then it's going to be really rough. So how do we start a problem like this? How do we begin in the field of chemistry to answer a question like this? Echo?
Figure out what formula to use.
So a lot of times a formula will guide us, right? And so what formula, what category of formulas were we looking for here, and which specific one?
Osmotic pressure.
Which is what type of formula? What category does it fall under as far as formulas? Colligative properties is kind of what I'm looking for, right?
I was going to say colligative, but I was
All right, so we've used it already today in class. Pi equals I M R T. The second step is really important. What do we know and what do we not know? By the way, I saw a lot of people using C instead of polarity. Don't do that. I was told that the book does it. I'll fire the book, and I'll have to pay off Humphrey for whatever I bet him. I don't remember what it was, but I bet him that wasn't true, but I guess it is true. Concentration is useless as far as a unit. It can be molarity, molality, percent mass, mole fraction, right? I want to make sure we're using the right set of units. So then the question becomes, which of the variables in that relationship, in that equation, do we know? So let's go through one at a time. Do we have the osmotic pressure given to us in the problem? Yes, it is 3.61 torr. Torr is a weird number. We'll come back to that. I. Do we know I?
1.
It's protein, so it's 1. Molarity. Do we know the molarity? We do not know the molarity. We do know the mass. We know the volume. But mass over volume is not molarity, right? It's moles of solute per liters of solution. R.
Yes.
Where's that? Where do you find that?
We need the tour for that one.
Okay, so I gave it to you on the back page. I will give it to you on the exam as well. Do you notice there's multiple versions of R?
Yes.
What's the difference between them? Units. You can use any one of them you want as long as it matches what you're doing in your calculations. All right, last one, temperature. Do we know temperature?
Yeah.
All right, so we can do that. We're good. So the only one we don't know is molarity. What are the ways that we can solve this problem now? I heard multiple different ways of doing it. Humphrey, how'd you go about it? When you say substitute it in, what do you do with it?
Multiply 63.4 by 1,000 to get it to grams per mole, and then you divide 21.5 milligrams by 1,000 to grams, and then you...
Oh, pause. So you're saying that if we wanted to know how many moles of solute we have, we could take the mass and then use the molar mass of either one of these.
No. Okay, so you take the 21.5 and you divide it by 1,000.
I think we're doing the same thing, right? So 63.4 thousand is what I have here, grams per mole. And I'm using the number of grams, the molar mass of wild type, and then this will give me the number of moles of the wild type. And then you can divide that by the volume, right?
That's in milligrams though, it's not in grams.
True, so it'll be millimoles
Yeah, millimoles.
or millimolar. Yeah, so what you're saying is you're more comfortable if I had...
That's just what I did. I mean, it works either way, but that's just what
Yep.
I did.
Great. So if we don't get rid of millo, we have to keep millo. Number of things keep straight. All right, so we can do this. So let's just keep in mind we're multiplying the mass by the reciprocal of the molar mass. Or we could say we're taking the mass divided by the molar mass to find the number of moles. All right, we'll come back to that in the next slide. So we can do this for each one of the two proteins. And then does it match either one of those if we take that number of moles divided by the volume, plug it in to give us osmotic pressure? Yeah.
It should match the Bangkok.
It should match Bangkok is what you found?
Yeah, it should. Yeah.
What did you get? What was your osmotic pressure? What R value did you use?
0.08205, that one.
And it didn't work. Why not? What happened?
Tour.
You used the atmosphere instead of torr. All right, so you could either convert torr to atmosphere, because 760 torr is 1 atmosphere, or you can use the other value of R.
I converted it. That's what it differs. So it differs equals 0.00475 ATM.
Okay.
I substituted that one for the osmotic pressure.
So did someone do it a different way? So what Humphrey's saying is that he took the approach where he said, well, I'll just guess and check. I'll use this as a molar mass. I'll use this as a molar mass. Find the molarity and see if that matches the osmotic pressure we had. How'd you do it?
Well, they gave us osmotic pressures 361.4. I used 361.4 as pi. We use I as 1 protein. Molarity gives us. Will we come back to that later?
Really, Mohammed? So use the one that applies to Tor.
Yeah.
Great. So then you solve for molarity. What do you do once you have molarity?
You have the amount of solution.
What did you get for your molarity first? Let's start there. If you solve for just molarity.
Hold on. 3.12 times 10 to the negative 7 mole.
All right. If we look at molarity, do we have either the moles of solute or the liters of solution?
Yes. We had a milliliters of solution.
So we know this. So if we know the liters of solution and we know what that ratio is, can you solve for the moles of solute?
Yes. That's what I mean.
You guys have questions on what I just suggested there? Is that what you ended up doing?
Sorry, I worked it that way. I said it wrong, but I worked it the way you just explained.
Okay. So if we know the liters of solution are, what do we have?
It's 1.50
0.00150 liters. Then we can solve for the number of moles of solute. What is your number of moles of solute? Oh, that's your moles?
Yes, and then I divided 21.5.
Okay, so the molarity is not this.
Yes, that's why I was saying I said it wrong.
Okay.
2.0812 times 10 to the negative 4.
2 point what?
0.0812 times 10 to the negative 4.
Okay. So for those of you who didn't do this approach, it is a bit janky the way we're talking through it. I apologize. So just to be clear, if we know everything in the equation except for molarity, we can solve for molarity. Once we know molarity, we know that it's moles of solute per liters of solution. So we can use that relationship, that is this, to find the number of moles of solute. If we know the number of moles of solute, can we find the molar mass?
Yes.
How do we do that, Chelsea? How do we find the molar mass if we know the number of moles of solute? What's the units for molar mass? Okay, do we know moles? We just found it. Do we know the grams? 21.5 milligrams, right? The molar mass is the ratio between the number of grams and the number of moles. What did you find as your protein in that case? What was the molar mass you found?
It was like 69.
68.9 thousand, I think, is what you'd find. So relatively close.
That's what I did. It was pretty close.
All right. So big picture, you guys have been working some problems on your own, but I want you to think about what's hidden within those units, right? We're talking about molarity, moles of solute per liters of solution. And if we just go back to what we had on the last page, in essence, what we're saying is that the moles of solute is the mass divided by the molar mass. I'll show that in more detail in the next slide. So this one was Bangkok J hemoglobin, if you use the numbers that I have up here. So let's talk through. I want you guys to take the change in, let's say, freezing point equation. Go ahead and write out that equation, and then we're going to unpack the units to show how we can find the molar mass if we had the change in freezing point and enough known. So write out the equation for that. I think we're getting to answer number 7, yeah. So can I have someone volunteer the equation? Carol?
It's molarity times 11 factor
Van Hoff factor.
The I is times K, which is the constant of.
And it's specifically to KF because each sample has both a freezing and a boiling point factor. All right. Where is molar mass hidden in that equation? Molar mass, molecular weight, I'm going to use those interchangeably. In molality, right? So if we're solving for an unknown, which unknown is it? And you have 4 different compounds, you can find their molar masses. It's hidden in there. So how would we, what are the units for molality? To be more specific, moles of okay? And what did we just say? How do we find the moles of our solute? If we have the mass of the solute
Divided by the moles. If we have the moles. Well, if we have the kilogram, we can solve it. Yeah, I got you.
So you're definitely gonna find moles. Masses over mass solute over moles of solute.
I thought we didn't know more.
all right, so I'm doing it 2 different ways here. If we want to know the moles of something, and we have the mass, we multiply the mass, well, we divide the mass by the molar mass, right? Grams per mole is the molar mass. So you take the mass of it divided by the molar mass. So the mass divided by the molar mass gives you the moles. You see how that's hidden within there?
No, can you say okay?
Basically taking this.
A lot of these you're going to get this much mass of an unknown is dissolved, and you see this change in colligative properties. So you'll know the mass of the solute. If we know the mass of the solute, if we knew the molar mass, we would just multiply the mass, well, divide the mass by the molar mass. Right? So maybe would it be easier if I wrote it that direction? Divided by the molecular weight, which is grams per mole. And maybe it's easier if I write out instead of mass, we can write grams. Grams divided by grams per mole gives you moles. Everyone okay with that part?
Yes.
So we want to know the moles. We know the mass, we don't know the molar mass. So then this unpacks into grams divided by grams per mole. This is this. The numerator is the same in both of these. So what we're saying is, if you know how to do algebra and rearrange an equation, we have within molality, we have moles of solute per kilogram of solvent, which is grams of solute divided by the molar mass divided by kilograms of solvent. It's all wrapped up in one. And this is true for molarity too. We basically just did the exact same thing with molarity. So I think I have this all written out here, which was supposed to be animated, and it wasn't. All right. So if we have the changing freezing point, Van Hoff factor, and KF, we'd have to know a lot of the different components, but if we did, we'd only have one unknown, that'd be molar mass. You can only use one equation to find one unknown. Right? You guys have taken algebra, college algebra. I'll feel pretty confident in that. So do you want to write, so if we were to write this out for osmotic pressure, what would that look like? Do you have a question, Caleb? What would it look like for osmotic pressure if we wrote kind of the same thing?
I is equal to I in parentheses. Let's come back to that.
Logan, you want to help out there?
Grams of solute divided by the molar mass divided by, it's
So osmotic pressure is molarity times
And then times the constant, okay. Yeah, that one.
Yeah, that one. All right. So I wrote down, instead of grams per mole, I wrote out molecular weight. So I'm just trying to show you the molecular weight. It's hidden within all these different equations. So you can either do it forwards or backwards. And so the way that you guys first described, that Humphrey described, was that you guys knew the molar mass of the two different options. So you plugged that in, took the mass divided by that molar mass to find the concentration factor, and then use that to see whether it matched. Totally cool. Or if you don't know what this is, don't have any idea, then you work backwards and just make sure you do order of operations right in order to get where you need to go. All right? So I'm just trying to hopefully set it up so that you you are less likely to write down some memorized version of this. If you forget it on the test, you can always figure it out. You can pull it out because you know how to solve for mass if you have molecular weight, or if you have molecular weight, you can find moles. Right, we can go back and forth between all those. Those are skills you guys have. All right. There are 4 minutes. This is true. Trying to remember what we have next. All right, so let's go ahead and do this problem. And I will start out class with a little bit of climate change relatability stuff on Monday.
He did that last semester. Just the first thing. You can do it either substitute or you can just throw it like in
Oh, I forgot. Acetic acid. Isn't that the sugar? Or am I lying? Doesn't it have sugar in it?
Oh, carboxylic acid, yes.
Okay. Because it has choo-choo in it.
Yeah. All right, spend another couple of seconds and make sure you focus on the process. What's the process, the approach you're going to use? We don't have time to answer the whole question. All right, so we have just a few more seconds left, so let's bring it together. An approach. So Logan, start us off on what you just said, and then we'll talk about how we go from there.
Use your freezing point equation.
Great, so we know it's a colligative property problem, we know it's a freezing point depression problem, so we write out our equations. And then, what do we do from there? Someone else. Josh.
Not a clue. I'm struggling on this. Actually, I have clues. I just don't know yet.
KF is almost like you have to just plug in.
Say again?
So it gives you the Nelson TI.
So we have... Alright, so we're almost out of time. The big thing next, what do we have what do we not have? We have delta TF. Do we have Van Hoff factors for these that we can figure out?
Yes.
So let's just go through them real quick. What are the Van Hoff factors start at A? 3.
2.
Ammonium nitrate. 2. And acetic acid is 1. All right. So we know what they could be. Do we know the molality of them?
No.
We know how much solvent. We know the mass, but we don't know the moles. Last, do we know KF?
Yes.
All right, we have a table in the back. We can look that up if we don't remember it. I will give that to you on the test. So can we rearrange this equation and find the molar mass? Kind of. What can we actually find? If we solve for an unknown,
That's molality, right?
so remember molality is grams divided by molecular weight divided by kilograms of solvent. Right? So do we know the grams?
Yes.
So we don't know molar mass, we know the kilograms of the solvent. But we don't really know I, right? So what we can find is a relationship between these two. So I suggest you guys try working this one on your own. Just because we're out of time. We are a minute and a half over. It might be easier to work from each individual one and test them out. Because you can find the molar masses for all those compounds, right?
Yeah.
That might be easier. And then you can see the relationship I'm talking about. It'll stand out to you once you've actually done it forwards. You can look at it backwards.
But like, come test time, that would take a really long time. If you know how to do like hard stuff,